Think about the stuff around you every day. You know, the metal in your phone, the glass screen.
Uh-huh.
What if these materials weren't always well fixed? Imagine one single substance that could be like a perfect conductor 1 second
Right.
and then a complete blocker of electricity the next. It sounds a bit sci-fi, but let's dive into this. Scientists at RIKEN have actually done something pretty amazing with molybdenum disulfide.
Yeah, exactly. This is some really fascinating work. We're talking about research led by Yoshihiro Iwasa over at the RIKEN Center for Emergent Matter Science.
Okay.
Their latest paper, it just came out in Nano Letters, October 21st, 2024. It shows this incredible level of control over molybdenum disulfide, MoS₂ for short.
MoS₂, got it.
And it's potentially, game-changing. So our mission here today is really to unpack the how and the why, how they manipulated it, and why it matters so much for future tech.
Okay, molybdenum disulfide MoS₂. It definitely sounds like something complex. What is it, like fundamentally, if we could zoom right down?
Okay, picture this. Incredibly thin sheets, just atoms thick, seriously thin.
Yeah.
You've got a layer of molybdenum atoms, and they're kind of sandwiched between two layers of sulfur atoms.
Okay, like a sandwich.
Exactly. But the cool part is how these atomic sandwiches stack up. They can stack in slightly different ways, and we call these different arrangements phases.
Phases, like water being liquid, ice, steam, that kind of thing.
Precisely. Same idea. And just like water acts totally differently as ice versus steam, OS2 in its different structural phases has vastly different electronic properties.
Okay, different stacking, different behavior. So what are the main phases we need to know about here?
There are two key ones, the 2H phase and the 1T phase.
2H and 1T.
Yep. The 2H phase is the most common, sort of its natural state. And electronically, it behaves like a semiconductor.
Ah, semiconductor is the heart of all our electronics, right? Transistors, chips.
Exactly. And that's why the 2H phase is already interesting. Professor Iwasa himself pointed out it's really promising for, next-gen semiconductor devices.
Okay, so 2H is our semiconductor. What about 1T? Is it similar?
Nope, quite different, actually. The 1T phase acts like a metal. It conducts electricity easily.
A metal. So same atoms, just stacked differently, and it goes from semiconductor to metal.
Yeah, and that duality, as Professor Iwasa mentioned, is pretty remarkable from a material science view. One material, two very different electronic personalities, just based on structure.
That is fascinating, like built-in versatility. But this RIKEN research, it goes beyond just observing these states, right? They're actually changing them, controlling the switch.
That's the core of it. They figured out a really clever way to do it using a special kind of transistor.
A transistor? How does that work here?
They used what's called a field effect transistor, connected to a tiny flake of this MoS₂, which started in its 2H semiconducting phase.
Okay.
Think of the transistor like a gate. By applying a voltage, a small electrical signal, they could control something else very precisely.
And that something else was?
It was pushing potassium ions into the MoS₂ layers.
Potassium, like the element. How does putting potassium in change things?
Well, these are potassium ions, charged atoms. By adjusting the voltage on that transistor gate, they could control exactly how many potassium ions squeeze their way in between those atomic layers of MoS₂.
Precise insertion.
Very precise. There's actually a picture in their paper, Figure 1, shows the setup, this little turquoise spot, which is the MoS₂ flake. You can sort of visualize it.
So they're doping it, essentially, but with ions, not just electrons. And they can dial in the amount.
Exactly. They're intercalating ions. And what happened as they increased the concentration of these potassium ions?
Let me guess. It changed.
Big time. The material underwent a phase transition. It flipped from that original 2H semiconducting phase to the 1T metallic phase.
Wow. Just by adding potassium.
Just by carefully adding the right amount of potassium. And they even figured out the ratio. It happened when there were roughly 2 potassium ions for every 5 molybdenum atoms.
2 for 5. That's incredibly specific.
It is. It shows this really clear direct link. Ion concentration controls the material's fundamental phase and behavior.
Okay, so semiconductor becomes metal. That's already a neat trick. But I feel like there's more to the story. Didn't you mention something even more exotic, like superconductivity?
Yes. This is where it gets really, really interesting. They didn't just stop at making it a metal.
Right.
They found that if they got that potassium concentration just right in the 1T phase, and then cooled the whole thing way, way down.
How cold are we talking?
Like incredibly cold.
Yeah.
Minus 268 degrees Celsius. Almost absolute zero.
Okay, seriously cold. And then?
And then the 1T phase became a superconductor.
Whoa. Zero electrical resistance.
Zero resistance, conducting electricity perfectly.
That's huge. Wasn't superconductivity already seen in MoS₂, though?
It had been, yes, but in the 2H phase and at a different temperature. Finding it in this potassium-induced 1T phase, that was unexpected.
Ah, I see. Different phase, different trigger.
Yeah, exactly. Professor Iwasa actually said that observing this superconductivity when they added the potassium was, for them, the biggest surprise of the whole study.
I can imagine. Finding superconductivity where you didn't necessarily expect it. Okay, so semiconductor to metal, metal to superconductor with cold and potassium. That's quite a journey for one material.
But wait, there's more.
Seriously, what else could it do?
Well, they found another surprising transition. This happened when they let some of the potassium ions leak back out of the 1T MoS₂. So the concentration dropped, but not all the way back to zero.
Okay. A lower concentration of potassium.
All right, relatively low levels. And then at a different temperature, this time minus 193 Celsius, still very cold, but warmer than the superconducting temperature. The material became an insulator. It stopped conducting electricity almost completely.
Hang on, so it went from metal to insulator just by letting a few potassium ions leave?
Basically, yes, by tweaking the ion concentration and the temperature in that 1T phase regime.
That seems incredibly sensitive.
It is. And Professor Iwasa noted this was also really interesting because, again, it wasn't something they had predicted. It just sort of emerged from the experiment.
So you have this one material, MoS₂, and by adding or removing potassium ions and changing the temperature, you can make it a semiconductor, a metal, a superconductor, or an insulator.
That's the essence of it. It demonstrates this incredible power you get from using ion insertion, in this case potassium, to control the structure, therefore the electronic properties of these 2D materials.
Yeah, and this technique, this ion insertion, it wasn't just a one-off trick.
Oh, no. Professor Iwasa mentioned his team has been developing and refining this kind of methodology for about a decade now.
A decade of work leading to this.
Yeah, and it shows the payoff. This method isn't just for finding weird new states, though that's cool. It's a powerful tool. It lets you explore the fundamental physics of things like superconductivity, these different electronic phases, and maybe even discover totally new superconductors.
It feels like unlocking a new level of control, doesn't it? At the atomic scale.
Absolutely. It's manipulating matter in a really fundamental way.
So let's just quickly recap the journey here. We start with molybdenum disulfide, MoS₂. Naturally, it can be a semiconductor, that's the 2H phase, or a metal, 1T phase.
Right.
Then, using this clever transistor technique, the RIKEN team precisely injected potassium ions. Enough potassium turned the semiconductor into a metal.
The 2H to 1T transition.
Then, with just the right amount of potassium in that 1T metal phase and cooling it down like crazy, boom, superconductor.
The big surprise, yeah.
And then letting just a few potassium ions leak out and setting the temperature a bit warmer but still cryogenic, it flipped again to an insulator.
Another unexpected twist.
It's like having an electrical multi-tool made from a single material. Semiconductor, metal, superconductor, insulator. Incredible.
It really is. The key takeaways are, 1, just how adaptable MoS₂ can be when you manipulate it like this, and 2, how effective this potassium ion insertion technique is for achieving that control.
And the potential implications.
Huge. This level of precision in tuning a material's electronic nature, it could really accelerate breakthroughs in next-gen electronics, maybe quantum devices, and definitely in the hunt for new and better superconductors.
It really makes you wonder, doesn't it? So here's something for you, the listener, to think about. If we can now manipulate materials at this fundamental level, switching their core electrical properties on command, what kind of devices, what kind of technologies does that unlock that maybe we haven't even conceived of yet? What possibilities are out there?
It's a fascinating question. And for anyone who wants to dive deeper into the actual science, the paper is in Nanoletters.